and to tell you some very exciting things about planets. So we just saw some amazing photos of the Keck Observatory, and this is a photo that's not particularly amazing because I took it from the front steps of my house, and the most prominent thing in the photograph are these power lines right there. But there's two other objects in this photograph which are hard to see. Luckily, I have a powerful laser pointer. One is the crescent moon, and even more difficult up here, you can see is the planet Venus. And so the camera that I used to take this was a 5-megapixel camera. I went to the computer and I zoomed in on it. I took pixels that involved Venus and I blew them up until I could see the individual pixels. And what's interesting about this is that when you look at Venus with your naked eye, it just looks like a very bright star. But with this slight amount of magnification, you can see that the picture of Venus has a kind of structure. It's not a perfect point of light. There's something going on there. And this is actually exactly the view that Galileo had when he first turned his telescopes to the skies about 400 years ago. This is a picture of Galileo, and you can see he's holding his small telescope right there, and these are pages of his notes. And so he was fascinated by Venus, which you can see in the early evening and the early morning skies. And he observed it for over a year, trying to figure out what it was that he was seeing. He had no idea what to expect. It was the complete unknown. And by the year 1610, this is more than 400 years ago, he finally figured out, or thought he figured out what was going on, but he wasn't quite sure. And like many scientists, he was very concerned about getting credit for his discovery. But at the same time, he didn't want to be embarrassed if the discovery was wrong. And so he came up with this clever solution for having his cake and eating it too. He took the answer to what he thought he was seeing, and then he scrambled the letters. And he did this in Latin. He was a very erudite guy. And he was good enough with Latin that he was able to re-scramble the letters into a new phrase, which had a subtle clue to what was going on. And so the anagram, if you can unscramble these letters, then you find the answer to what he was seeing through his telescope. And so the Latin translation here is, "These are at present too young to be read by me." The question is what do those letters unscramble to form? He released the answer on New Year's Day dramatically in 1611. And I can tell that you all are completely enlightened by his answer. It turns out that not only, even if you are an expert with Latin, even if Latin is nobody's native language, but even if Latin is your second language, it's hard to understand what's going on. The translation to this is that the mother of love imitates the figures of Cynthia. What can that mean? The mother of love is Venus, and Cynthia is the Roman name for the moon. And so what he is saying here is that Venus exhibits phases like the moon. By observing repeatedly through the course of the year, he was able to see that Venus is going through phases. But it's different than the moon in the sense that when Venus is near the full phase, it's much smaller in the sky. And when it's near the crescent phase, it's much larger in the sky. What this shows, the only way to understand these results, is if Venus is going around the sun in an orbit that's smaller than the Earth's orbit. That realization had tremendous power because it proved, by looking through the telescope, it proved that the Earth wasn't the center of the universe. It proved that things aren't all going around the Earth, that the planets are going around the sun. And that allowed a tremendous shift in understanding and viewpoint. And it's also exciting at that time to think of what is Venus. Galileo realized Venus is a world of a similar size to our own world. And for many years, for hundreds of years, as a matter of fact, Venus through a telescope, it gave this complete kind of mask of mystery. Venus is entirely covered by white clouds. And it just presents this mysterious figure in the telescope. So even up to a time that was not far before when I was born, it was scientifically credible, it was possible to think that beneath those clouds there might be something like this. Wouldn't that be cool? That would be an amazing thing. There was a time in the late 1940s and the early 1950s when it was possible to think realistically about space flight. Wernher von Braun, after the Second World War, was hard at work designing the rockets that eventually became the rockets that went to the moon. They had plans for how to go to Mars. You could really talk realistically about space travel within the solar system. And for a brief window of a few years, there was a possibility that beneath Venus's clouds, there might be something like this photograph right here of Kauai. Unfortunately, or perhaps fortunately, that's not the case. The surface of Venus is hot enough to melt lead, and the air is 100 times thicker than here on Earth, and you would die instantly if you were transported to the surface of Venus. Now this is kind of supposed to be a positive talk, so I won't dwell on that depressing prospect of a visit to Venus. You know, there's, I think probably in this theater, they probably had the Martian may have played the big blockbuster movie about the astronaut who is isolated on Mars and awaiting a rescue. There's never going to be a blockbuster movie about Venus. There's no plans to visit Venus or anything like that. It's extremely close to the Earth in size. It has an atmosphere, but it's completely uninhabitable. Our own solar system, if we want to find planets like this, it's now clear that we have to look to the stars. Our own solar system has the Earth, which is a fabulous planet, but the other planets don't measure up. They're uninhabitable. And there's this kind of very interesting parallel, I think, coming to Hawaii got me thinking about this, about the search for other worlds. If you look at the Pacific Basin, this is just a picture that I made off of Google Earth this afternoon. The southern part of the Pacific Basin is completely studded with islands. And the Polynesian voyagers knew, they had an expectation that there were wonderful islands beyond their horizon. They had incredible faith in that idea, and they were willing to risk everything to find these new worlds like the one that we're standing on right now, the big island of Hawaii. There's just amazing bravery and fortitude in the journeys that they undertook to find these amazing places and to make them their own. It's interesting to look at Hawaii. This is another picture from Google Earth. And we're, of course, on the Big Island, somewhere right around there. The Big Island is, of course, the youngest of the Hawaiian Islands. And as you go northwestward up the chain, everybody knows that the islands get older and the volcanoes die out. Haleakala last erupted a couple hundred years ago. And I've been to Kauai, and the ancient Hawaiians also knew that there was something fundamentally different about the islands as you go up the chain. It was understood in in sort of the folklore of the islands that Kauai was an older place and that the island of Hawaii is the newest. And that's true, right? If you go to the canyon on Kauai, you can see that the whole island is bleeding red into the ocean as the volcanic soil is washed away by the tremendous rivers that flow down from the rainforest. And the ancient Hawaiians would have embarked to the north, away from Hawaii, in search of more worlds. And they came across the next one in the chain is Nihoa. Nihoa is only about a mile across, and people were able to live there for a few hundred years, but they were not able to hang on. It's just not large enough to support a society. It's just not a large enough island. There's problems with the water, there's problems with the soil. And if you go further up the chain, I'm sure that nobody here in this room has been to Necker Island. And Necker Island is just a few acres in size. It has barely just a little bit of grass on it. And then the last island in the Hawaiian chain that actually has lava rock is the Cruz Pinnacle. This is about 300 miles northwest of Kauai. And it literally and figuratively looks like a sinking ship. It's slowly settling beneath the waves. And so there's this kind of remarkable opportunity because Hawaii is really the first sort of habitable planet that was discovered in some metaphoric sense by the human race. And the fact that the Keck telescopes are sighted upon the highest point of this island, facing out towards the stars, is this sort of amazing coincidence, I think. It's the best place in the world to search for new worlds. And in some sense, there's a limited amount of time. In 10 million years, the island, the big island of Hawaii, is going to look like the Cruz Pinnacle, and new islands will have taken its place. And so, in some sense, one can think that there's opportunity to seize an opportunity and to find out what's out there among the stars and to ask the question, are there planets like our own out there? It's important to get a sense of scale. I'm an astronomer, but it's difficult even for me to understand just how large the distances between the stars are. And so an analogy that I like is to take a penny. And if we imagine that we shrink the entire Earth down to the size of a grain of sand, then the sun at that scale is roughly the size of a penny held at arm's length. So I have a grain of sand in my fingers, but it's too small for you to see. And you can just barely see the penny that's in my left hand. And so a scale model of the solar system is not a very exciting demonstration. It's just a grain of sand representing the Earth to scale and a penny. And over the course of a week, the grain of sand moves from where I have it right now to about right there. And that takes an entire week. And if we wanted to have a really boring public lecture, we could do a demonstration where I would stand here for an entire year. And during the course of the entire year, the sand grain would go around the penny. Now I know that, I don't know for sure, but it seems like this town is a kind of a laid-back place. It seems like the kind of place where you can go and get away from the kind of things that make my own life stressful. I have hundreds of emails on my phone because I'm gone for 2 days, lots of phone calls, lots of, just all sorts of things I'm supposed to be dealing with. And at times like that, it's sometimes good to remember that it's really just like a sand grain going around a penny once per year. That's a great way to kind of reset your perspective. But I think in this town, it's not so important to teach that lesson. I think that there's a better balance here. And so the size scale in our solar system is pretty spread out. sand grain sized Earth is a pretty spread out setup. But what's really remarkable is the distances between the stars. To kind of get a handle on the distances to the stars, you have to take the penny, which represents the sun, and then shrink that down to the size of a grain of sand. That amounts to almost a trillion-fold decrease in the size of the sun. And once you do that, once you shrink the sun down to the size of a grain of sand, then you can start to get a handle on the distances between the stars. If the sun is the size of a grain of sand, then the nearest stars are about 6 miles away. The nearest stars are not much closer than the summit of Mauna Kea. It's like grains of sand separated by miles. So when you see pictures of a galaxy, what you're seeing is something like a box full of sand, a box maybe this large, where the sand grains have been spread out over a distance that's thousands of times larger than the continental United States. It's just an incredible amount of empty space. And so you might wonder, how can something that's that rarefied look that amazing? And the reason why is because photographs like this are taken with the most powerful cameras that we have. Cameras like the ones on the Keck telescope, or in this case, a picture that was taken from space. We have to use the longest time exposures with our largest cameras in order to see this incredibly ephemeral and rarefied detail. If you're actually looking at a galaxy, it looks like that. There's some sort of light on the screen which is not the galaxy. You can't see it. In fact, it has to be extraordinarily dark in order to really see whether a galaxy is there or not. And again, island of Hawaii is perfectly suited for that. Out in the middle of the Pacific Ocean, the skies here are incredibly dark, which is one of the things that makes this an amazing location for the Keck Observatory. In order to understand whether there are other planets out there, we kind of have to have a handle on how they form. And so we've learned over the past half century that stars and planets condense out of clouds of gas and dust. And we can take pictures of these clouds of gas and dust that will give rise to solar systems. This is a kind of a very mysterious one. This is a cloud of gas and dust that's roughly the mass of our sun, sort of spread out into a cold agglomeration that's about a half a light year in size. And this thing, this black cloud, is blotting out the stars that are behind it. You see it more as a negative image than as a positive image. And we can study the interior of this black cloud by looking at the radio waves that it gives off. And what we see when we peer inside this cloud is that it's not a calm situation. The gases are roiling and boiling, and there's magnetic fields, and the magnetic fields are trying to hold this cloud up against the inward crush of gravity, but they're not really managing to do that very well. And this cloud is slowly, gradually collapsing under its own weight. And if we came back in about 1 million years, this cloud would have turned itself into a solar system. It's an amazing thing that a cloud of gas and dust can give rise to this, to a theater full of people thinking about what's out there. We started out 4.5 billion years ago looking like that. The first sort of attempts to understand the formation of the world in terms of kind of a logical or rational worldview date back to the 1700s with some of the great French scientists. This fellow, Georges Leclerc Buffon, he thought he knew everything, and he was set to write a 47-volume encyclopedia about all knowledge. I think he got through 36 volumes before he died, and the problem was that the early volumes were already obsolete before he was finishing the older ones, right? So it's kind of a cautionary tale. He had an incorrect idea about how the solar system formed. He thought that there was a close encounter with another star that pulled the material that turned into the planets out of the sun, and that's not actually what happened. The first ideas that gave a sense of what really happened were evinced by Immanuel Kant, of all people, and Laplace in the 1700s. And what they realized was that the sun and the planets formed out of a spinning disk of gas and dust. And they wrote about this. Laplace did lots of calculations, and they weren't very well received. You guys seem to be a very respectful audience, and so I'm talking about how the solar system formed, and I can see people nodding, and people aren't jumping up and down and getting angry. But the third president of our own country didn't like this stuff. There's a quote from Thomas Jefferson, who was actually one of our more erudite presidents, and he said that in reference to these ideas that Laplace had, he said that dreams about the modes of creation, inquiries whether our globe has been formed from the agencies of fire or water, how many millions of years it has cost Vulcan or Neptune to produce what the fiat of the Creator would effect by a single act of will, are too idle to be worth a single hour of any man's life. You can see that Thomas Jefferson didn't think very highly of these kinds of ideas, and indeed, it takes a certain leap of imagination to think of a cloud of gas and dust giving rise to worlds. But it does happen. And we see it happen. This is, I'm supposed to be talking about the Keck telescope, but I'm showing a couple of Hubble Space Telescope images. This is a picture of a solar system that is in the process of forming. If you look at this picture, what you're seeing in the background is glowing hot gas. And in the foreground is cold gas, and this gas is actually in the form of a disk, kind of like a donut. And in the center of the donut, you can get just a little sense there's kind of a red glow in there. That's a newborn star that's being hidden by this gas and dust that's orbiting around it. And the picture on the right is just a computer simulation of how that process works. If we put our own solar system here, Pluto's orbit would be inside this ellipse. This is one of the furthest known objects in our solar system, the new planet 9, which made a huge news splash a week and a half ago. It has an orbit, if it exists, it's about the size of this swirl that I'm making with the laser pointer. And so these solar system-sized objects are out there and they're forming, and the gas is whirling around the star, and the gas has lots of dust in it, and the way that the dust builds itself into planets, the way that that gets going is something that you can observe here on Earth. If you have a hardwood floor and you don't sweep or vacuum under the bed, then dust starts to build up. Have you guys ever seen that? It does happen. And it's interesting to watch how the dust builds up. You might think that it would build up in just a very steady layer, but that's not what happens. The random currents of air under the bed make dust bunnies. Right? They make these kind of weird, fluffy aggregates. It's interesting if you put a dust bunny on a scanner or make a close-up photograph of it, you see it has this weird fractal structure. And that's actually what happens in the earliest days of our own solar system. The dust agglomerates into these dust bunnies, for lack of a better word, and the dust bunnies become larger and larger. You can accumulate dust bunnies under your bed in just a week or two. And so you can imagine how big that they would get in a million years. They effectively turn into planets. And some of them get so large that they start grabbing gas from the disk and turn into gas giant planets. And so at the end of the process, we end up with a planetary system. This is not a scale model. This is just a kind of a representation of where the planets were at 4 o'clock this morning when I was preparing the talk. And so let's look at the inventory of our solar system. Right now we've got Jupiter and Saturn. Jupiter is about 319 times the mass of the Earth. It's mostly made of hydrogen and helium. It has no solid surface. It's a huge behemoth of a planet. There's a type of planet that's represented by Uranus and Neptune. This is to scale. So these planets are to scale. This is the Earth, and you can see that Neptune is about 4 times the size of the Earth. And then we also have these icy outer dwarf planets, objects like Pluto and Eris that are out in the outer solar system. That's our inventory of planets, and that's what we thought we would find around other stars. And finding planets around other stars is hard. One reason why it's hard is because the stars completely drown out the light of the planets. Like right now, I'm having a hard time seeing you guys. And the reason is because there's this brilliant light shining in my own eyes. And so I can't really see the audience. Probably it's a good thing. Probably you guys are sleeping and I just going on my own and I can't see, I'm disconnected. And that's a little bit what like searching for planets through a telescope is like. It's, you get blinded by the glare of the central star. And at Keck, they have partially solved that problem. They're now finding planets that are glowing in their own heat around young stars. And the way they do this is they block out the light from the star very effectively. And then they look carefully around the blocked light and find these planets. And so in this picture right here, this is kind of the residuum that's left after they've blocked out a huge fraction of the light of this nearby star. And when they do that, the brilliant glare is reduced to this weird speckle pattern, and they can pick out the planets that are orbiting. This was a really exciting discovery done through this technique of adaptive optics. And this is sort of the roadmap that we need to find planets like Jupiter, or the roadmap that we thought we needed. Something happened that kind of short-circuited that mode of discovery. In 1995, these two gentlemen, Didier Queloz and Michel Mayor, they're from Switzerland, using a small telescope, observing this star in the Great Square of Pegasus, which you can almost see with your naked eye, they found a planet. The way they found this planet was very different from the way of taking a picture through a telescope. What they did was they measured how fast the star was moving. So if you have a planet that is going around a star, the planet makes a large circle, and the star makes a small circle, back and forth. It's as if they're both orbiting around a point of balance. And so by carefully looking at the light of the star gets redder when the star is going away from you, it gets bluer when it's going toward you. They were able to infer that there was a planet that was similar to Jupiter that took only 4.5 days to go around the sun. Jupiter takes over 3,000 days to go around the sun, and this first planet that they found takes only 4.5 days. It came as a complete shock, complete surprise, and they were greeted with complete skepticism. Nobody believed it. And this is a crazy planet. If you were actually there, and you had number 14 welding glasses on, it would look something like this. The day side of this planet is absolutely brilliant. It's about 400 times brighter than the daylight outside here would be on June. And the night side is so hot that it would be glowing like red hot coals, literally. And so these storms on the night side are like hurricane force, but in addition to being hurricane force, they're glowing red hot. It's be quite a dramatic sight if you could observe it from a safe distance, a little bit like going to the Volcanoes National Park. And we've discovered a huge number of planets now. I know it's not a good idea to show graphs and equations in the evening talks, right? It's a sure recipe for putting people to sleep. But I'll show one here anyway. This graph has the mass of the planet, the mass ratio actually, plotted here, and the period, the amount of time that it takes to go around the sun or its parent star here. And so what we see is this huge family, this huge population of planets. And what's interesting is that these planets look nothing like the ones in our own solar system. Our solar system planets, this is Venus, and this is the Earth on this diagram. And then this is Jupiter out here. Mars and Mercury are too small to even show up. They're down somewhere down here. And Saturn, Uranus, and Neptune are off the graph over here. And so what we found is that the average planetary system in the galaxy looks nothing like our own. And we're not quite sure what to make of that yet. It's true. We can certainly speculate, right? So you can talk about how many Earth-like planets are out there and so forth and so on. But those still have a kind of air of speculation to them. These are the facts. And the facts is that our own solar system seems to be unusual. Now, another thing that makes many of these planets unusual is that their orbits are eccentric. This is a model of the orbit of Mercury. Mercury's orbit is not quite a circle. So this gray line right here is a circle. This is the center of the circle. Mercury doesn't follow the gray line. It actually goes around the sun in a kind of slightly egg-shaped, slightly off-center ellipse. But it's pretty close to the circle. And Mercury is the most eccentric planet in our solar system. Now, if you make an orbit more eccentric, then it gets even less like a circle. And something that's interesting, this is an eccentricity of 0.4. It's sort of 40% of the way there. And this planet spends more time far from the star than it does close from the star. The way that this is plotted is an equal amount of time between each dot. You can see that the dots are more spread out here than they are there. And it gets more extreme. Here's an orbit with an eccentricity of 0.6. No one is going to mistake that for a circle. And here's an eccentricity of 0.8. And here's an eccentricity of 0.9. So I actually made a scale model here. So what I did was I printed out the orbit on a piece of paper, and I put the sun, I used a kumquat for the sun, and then I used a red peppercorn for the planet. And then what I did is I took my camera, the same one that made that picture of Venus, and made a stop-action film to show how the orbit works. All I did was I made 100 pictures of the kumquat, of the peppercorn, as it traces its path around the kumquat. And you can see that I made a mistake on one of the frames. You can see my hand with the tweezers as I move the peppercorn. And so this orbit is interesting. The planet spends a long time out here, and then it goes whipping through its close approach to the star. So it gets blasted by the sun during its close approach, and then it kind of freezes when it's far out. And in fact, this is a model of the planet that actually exists, that has been studied from Keck. This planet, HD 80606b, has the most eccentric orbit known. And so if we have our own solar system, here's the orbit of the Earth, here's the orbit of Mercury, and then here's the orbit of this planet. This is what this planet would be doing if it was in our solar system. It takes 111 days to go around the star, and it goes just crazily whipping through the periastron, close approach. This shows some details of that. And the weather on this planet is just awful. It's just, I might complain about how it rains here all the time, but during the course of an orbit on this planet goes from 260 degrees Fahrenheit, which is not comfortable, to 1500 degrees Fahrenheit, which is really not comfortable. Just an awful, awful place. And there's other interesting things about the planets that we're finding. This particular system has 2 planets which are tracing their orbits in an interesting way. And so I'm going to indulge you with another movie. It is actually a movie theater here, actually, after all I hear it. So here's another movie. This is a green peppercorn and a red peppercorn, both tracing these orbits around the kumquat. And what happens here is that the orbits have arranged themselves. They talk to each other. One goes around, on average, 2 times for every 1 time the other one goes on. But it's not a perfect match. They kind of get ahead and then fall behind. They rock back and forth. This is a more scientific view of what goes on over thousands of years. You see the orbits are kind of jostling each other back and forth. They never get completely out of whack, but they're never entirely happy either. And with Keck, we found a number of kind of crazy, weird planetary systems. Again, looking nothing like our own, where the orbits are talking to each other quite radically. Now, when they were setting up this talk about an hour and a half ago, they were playing some pretty cool music through this sound system. And I was, wow, this big JBL cabinets produce an awesome sound. And so I quickly thought, wouldn't it be cool if we could turn this orbital motion for these kinds of systems into a sound wave? So what's going on is the planets are going around the star. The star is going back and forth along the line of sight. And so you can take that back and forth motion and interpret that as a sound wave. And you can listen to what these planetary systems sound like. Interesting that you can't see what's on my screen, but that's fine, because I want you to listen to these planets that I've computed. So the first one I'm going to play is extremely boring. This is what a simple circular orbit turned into a sound wave sounds like, right? So I'm not giving this any advanced hype. It's extremely boring. It's just a way to set up your expectations for what are to come. So hopefully this will work. Yeah, it works. I mean, it sounds like there's feedback on the microphone. Let's try that again. There is no feedback on the microphone. It just sounds like it's an awful non-musical tone. I mean, it's not awful in the sense it's not grating, but it's just completely boring. It's just a sine wave. The signal that a single planet makes if you interpret it as sound, the orbit. So you can do more interesting things. One interesting thing is to take Earth and Venus. I was talking about Venus earlier. I was talking about Earth earlier. Venus and Earth are going around the sun, and they make the sun wobble back and forth over the course of years. And so if you take that motion, interpret it as a sine wave, and speed it up radically so that you can hear it, then you can hear the interaction that Earth and Venus have. And this is also not particularly exciting. Let me just play it. But it's better than the sine wave, right? It sounds like kind of a boring flute-like tone. And the reason why it's not that bad is because it's close to a 5 to 8 commensurability. Earth goes around the sun about 5 times for every 8 times that Venus goes around. Now, if Venus and Earth got a lot more massive, if Venus and Earth were pumped up, kind of Arnold Schwarzenegger style, so that they were hundreds of times more massive than they are, then they wouldn't get along very well. And the motion that they would create would be quite different, and the sound would get more interesting. So this sound is what happens if you make Earth and Venus the size of Jupiter. Now, it's not that much different, but if you listen to it, you hear this kind of a warble. especially near the end. There's kind of an unsteadiness to that. The two planets are not happy about that orbit, but they're not getting out of control. What's interesting is if I increase the mass just a little bit more, then strange things start to happen. So here, I've increased the mass to about 10% larger than Jupiter for both planets. So they're really throwing each other around, and that's reflected in that weird unsteadiness. And then if I really crank it up by another 10%, that ending, Earth got thrown out of the solar system. That was it, that was the end of the sound. Now, in many of the systems that we're finding, so that won't happen. Earth and Venus won't have their masses increased by a factor of 400. And so that particular disaster literally can't happen. But what we find when we look out there at the orbits that do exist, planets that are happy with each other are in what's called a mean motion resonance. And a mean motion resonance sounds exactly like it sounds, if that makes any sense. So one of my favorite planetary systems, and this was discovered at Keck, and it's been characterized at Keck over the last 15 years, is this nearby red dwarf called Gliese 876. Gliese 876 makes a remarkable, remarkable sound if you sonify the waveform. It literally has this deep, resonant tone. There was somebody, I was standing outside looking at my many emails, and somebody was complaining. I was like, oh, I thought Star Wars was going to be shown in here, and just some guy from Santa Cruz can't get away from it. That's literally what he said, but this does sound something like the beginning of Star Wars. I don't know if you guys saw Star Wars. That was a great movie back in the 70s. But remember how like those giant ships were roaring? It was those kinds of sounds, and that's a real planetary system turned into a sound wave. I'll play just one or two more. I did this experiment where I kind of set up thousands of planetary systems to see what kind of sounds would show up. And when you do that, you get some bizarre sounds. This is not a real planetary system. This is just something that could be out there. And it's unstable, so it does weird things. It's just like, it almost be kind of a good ringtone, right? I mean, it's like you'll know it's your phone ringing. Here's one more example of an unstable planetary system. It's just bizarre. And so if you look at a movie of that, the planets are just throwing each other around. It's totally crazy. And that happens. Planetary systems, many planetary systems don't survive their formation phases, and they do stuff like that, and planets get ejected from the solar system, and it's game over. So it seems like that almost happened in our solar system for one of the planets. I put this slide up with a great deal of pride because Constantine Batygin was my student at Santa Cruz, and he was a brilliant guy. He went to Caltech and got his PhD in 3 years, and he was so good that they immediately hired him as a professor there. As soon as he graduated, they were just like, sign right here. And then he did a lot of work that looks like this. And what he realized is that there seems to be another planet in our own solar system that we haven't discovered yet. They call it Planet 9. And he worked with Mike Brown, is an observer who uses Keck to search for objects in the outer solar system. And so they collaborated to realize that there's very, very likely another 10 Earth mass planet in our own solar system. And this caused a huge stir. Something that's amazing is this is the paper. And then in just over a week, this is the number of downloads of the paper, 280,351. So this is like the only time that I know of that a paper that's full of stuff like this has gotten download numbers that exceeded the top downloads on iTunes. So this was a larger number of downloads than, for instance, Adele got last week. So there might be hope after all. So this Planet 9, it's inferred to be there because it seems to be pushing the orbits of all these guys over into a particular direction. These outer solar system objects like Sedna, are all being forced into eccentric orbits that are all more or less aligned on one side of the solar system. And this can be best explained if there's an unseen planet which is traveling in this highly eccentric orbit. The orbit has an eccentricity of about 0.6. It takes about 20,000 years, 18,000 years to go around the solar system. And our whole solar system that we're familiar with is buried down in here. This is the orbit of Pluto and Neptune, and we're all right down here by the sun. So this is this weird planet that would have gotten tossed out early on, or almost tossed out, by rough interactions between the precursors of Jupiter, Saturn, Uranus, and Neptune. So it's pretty exciting about whether this exists or not. This is close to my last slide. I have a website called Metaculus, www.metaculus.com. Now what you can do here, and I urge you to do this, you can go to the website and you can make predictions about whether you think things are going to happen or not. So one of the prediction markets that we're running on this website is, will Planet 9 be discovered in 2016? Interestingly, if it does get discovered this year, it will almost certainly be discovered from the top of Mauna Kea. And so I don't want to try to act like a candidate up here and urge people to vote in a certain way. But my own vote here was 68.3%. I think there's a 68.3% chance that this planet is going to get found. And that's not just because I was Constantine's professor, it's because I do think that there's not a 100% chance that it's out there, but there's an excellent chance that it's out there. So even if you don't want to vote, go to the website and check out how the voting is evolving. Right now, the prediction is that there's a 59% chance that it'll be found this year. Hunches are fine. There's experts on the site, but then there's also, if you have a hunch, even if it's completely just a hunch, you won't screw things up by voting. It's interesting to see what everybody thinks. This is that picture of Venus that I showed in the very beginning with just this kind of hint of structure. And we're left with this desire to know more. We know about Venus, but we don't know very much about the extrasolar planets. And the Keck telescopes can help to get us there. So I'll stop there and take any questions that you might have.